Good evening. Two NASA spacecraft, Messenger in orbit around the planet Mercury and Venus Express, end their missions this month. The probes have been amazingly successful, and today we know far more about Mercury and Venus than since the dawn of the space age. The region between the orbits of Mercury and the Sun is frequently visited by comets, and on occasions these can be seen falling into the Sun on images beamed back from NASA's SOHO spacecraft. Other comets simply disintegrate, like that of Ison in January 2014. So there is plenty of rocky debris around to impact on the planet Mercury to form craters. And on rare occasions, very large impactors arrive, one of which created the Colaris Basin, one of the largest impact basins in the solar system, while another hit Venus hard enough to turn the planet upside down. The planet Mercury is named after the Roman god Mercury, the messenger carrier, with winged sandals. It is the closest planet to the Sun, lying at a mean distance of 57.9 million kilometres, speeding along its orbital path at more than 47 kilometres a second. In terms of size, it is not much bigger than our Moon, and its appearance is very similar. Mercury is 4,880 kilometres in diameter and is mainly covered with impact craters. A day on Mercury is 58.6 Earth days long, which is slightly less than the planet's year of 87.9 days, which makes it synchronous, just like our Moon, which always keeps one face turned towards the Earth. Mercury is gravitationally locked and rotates in a way that is unique in the solar system. As seen relative to the fixed stars, it rotates exactly 3 times for every 2 revolutions it makes around its orbit. As seen from the Sun, in a frame reference that rotates with the orbital motion, it appears to rotate only once every 2 Mercurian years. An observer on Mercury would therefore see only one day every 2 years, which makes the calendar very strange indeed. There is no area of permanent daylight, no region of permanent night, and no twilight zone. Since Mercury is so small and close to the Sun, it is generally hard to find either in the dusk sky after sunset or the dawn sky before sunrise, even though its magnitude can equal that of the brightest stars. Also, its maximum angular diameter can never be more than 13 arc seconds when it is at its best, when the planet is closest to the Earth, at about 82.5 million kilometres. Therefore, Mercury is a telescopic disappointment, since large telescopes are needed to glimpse any detail on the planet, although its phases can be viewed in moderate-sized telescopes. Much of what we know about Mercury comes from images and observations sent back by 2 NASA spacecraft. Mariner 10, which was launched on the 3rd of November 1973 and flew past Mercury on 3 occasions at an average distance of 200 kilometres. Twice in 1974 and again on the 16th of March 1975, along with the Messenger mission, which is due to come to an end soon. Mariner 10 was the mission of many firsts. It was the first spacecraft to visit Mercury, the first to use a gravity assist, and the first to visit more than one planet. Mariner 10 passed Venus on February the 5th, 1974. I will have more to say about this later in the programme. It was also the first to make multiple flybys of a planet, in this case Mercury, and the first to use the solar wind for orientation during its flight. Owing to the geometry of its orbit, the same side of Mercury was sunlit each time, so Mariner 10 was only able to map 40 to 45% of Mercury's surface, taking over 2,800 photos. It revealed a more or less moon-like surface. It thus contributed enormously to our understanding of the planet, whose surface had not been successfully resolved through telescopic observation. Mariner 10 also discovered that Mercury has a tenuous atmosphere consisting mainly of oxygen, 42%, as well as a magnetic field and a large iron-rich core. The atmosphere of Mercury is essentially a vacuum. Composition values are variable and the values are not well controlled. This is due to the Sun's heat constantly changing as the planet orbits around the Sun. At perihelion, Mercury is 46 million kilometres distant from the Sun and 69.8 million kilometres at aphelion, a difference of 23.8 million kilometres. This affects the planet's overall temperature and the density of the thin atmosphere. Sunlight and the solar wind constantly blow away Mercury's atmosphere into space. It therefore also depends on whether the Sun is at solar maximum when the number of flares are at their greatest, as they are at the moment. This affects the level of solar wind streaming over the planet. Mercury's thin atmosphere contains oxygen, hydrogen and helium, along with smaller amounts of sodium, potassium, calcium and magnesium. Mercury's density is the second highest in the solar system, at 5.4 grams per square centimetre, only slightly less than the Earth's density. Mercury's density can be used to understand details of its inner structure. Although the Earth's high density results appreciably from gravitational compression, particularly at the core, Mercury is a much smaller planet and its inner regions are not as compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. Geologists estimate that Mercury's core occupies about 42% of its volume. For Earth, this proportion is 17%. Research published in 2007 suggests that Mercury has a molten core. Surrounding the core is a 500 to 700 kilometre mantle consisting of silicates. Based on data from the Mariner 10 mission and Earth-based observations, Mercury's crust is believed to be 100 to 300 kilometres thick. One distinctive feature of Mercury's surface is the presence of numerous narrow ridges, extending up to several hundred kilometres in length. It is believed that these are formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Mercury's core has a higher iron content than that of any other major planet in the solar system, and a number of theories have been proposed to explain this. The most widely accepted is that Mercury originally had a metal-silicate ratio similar to chondrite meteorites, thought to be typical of the solar system's rocky matter, and a mass approximately 2¼ times its current mass. Early in the solar system's history, Mercury may have been struck by a planetary body several thousand kilometres across. The impact would have stripped away much of the original crust and mantle, leaving the core behind as a relatively major component. A similar process, known as the giant impact theory, has been proposed to explain the formation of the Moon. The radiometer readings of Mariner 10 suggested that Mercury has a nighttime temperature of minus 183 degrees centigrade and a maximum daytime temperature of plus 187 degrees centigrade. Mercury's surface is similar in appearance to that of the Moon, showing extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. Because our knowledge of Mercury's geology has been based only on the 1975 Mariner flyby and terrestrial observations, it is the least understood of the terrestrial planets. Mercury was heavily bombarded by comets and asteroids during and shortly after its formation 4.6 billion years ago, as well as during a separate subsequent episode called the Late Heavy Bombardment that came to an end 3.8 billion years ago. During this period of intense crater formation, the planet received impacts over its entire surface, helped by the lack of any atmosphere to slow impactors down. During this time, the planet was volcanically active. Basins such as the Calaris Basin were filled by magma, producing smooth plains similar to the Maria found on the Moon. Data from the October 2008 flyby of Messenger gave researchers a greater appreciation for the jumbled nature of Mercury's surface. Mercury's surface is more varied than either Mars or the Moon's, both of which contain significant stretches of similar geography, such as Maria and plateaus. NASA's spacecraft Messenger was launched in August 2004 to study Mercury's chemical composition, geology and magnetic field. It became the second mission after Mariner 10 to reach Mercury when it made a flyby in January 2008, followed by a second flyby in October 2008 and a third flyby in September 2009 before entering Mercury's orbit in March 2011. On the 3rd of July 2008, Messenger team member Thomas Zurbuchen announced that the probe had discovered large amounts of water present in Mercury's slight atmosphere, which was an unexpected finding. Messenger also provided visual evidence of past volcanic activity on the surface of Mercury, as well as evidence for a liquid planetary core. Messenger's formal data collection mission began on the 4th of April 2011. By the time the primary mission was completed in March 2012, close to 100,000 images had been returned to planetary scientists. On the 5th of October 2011, the scientific results obtained by Messenger during its first 6 terrestrial months in Mercury's orbit were presented in a series of papers at the European Planetary Science Congress in France. Among the discoveries were the unexpectedly high concentrations of magnesium and calcium found on Mercury's night side, and the fact that Mercury's magnetic field is offset far to the north of the planet's centre. In November 2012, NASA reported that Messenger had discovered both water ice and organic compounds in permanently shadowed craters at Mercury's North Pole. In February 2013, NASA published the most detailed and accurate 3D map of Mercury to date, and assembled from thousands of images taken by Messenger. Craters on Mercury range in diameter from small bowl-shaped cavities to multi-ringed impact basins hundreds of kilometres across. They appear in all states of decay, from relatively fresh rayed craters to highly ruined crater remnants. Mercury's craters differ from lunar craters in that the area blanketed by their ejecta is much smaller. This is a consequence of Mercury's stronger surface gravity. The largest known crater is the Calaris Basin, with a diameter of 1,550 kilometres. The impact that created the Calaris Basin was so powerful that it caused lava eruptions and left a concentric ring over 2 kilometres high surrounding the impact crater. At the antipod of the Calaris Basin is a large region of unusually hilly terrain known as the weird terrain. This antipod is the point on the planet's surface directly opposite the Calaris Basin. One theory for its origin is that shock waves generated during the Calaris impact travelled around the planet, converging at the basin's antipod 180 degrees away. The resulting high stresses fractured the surface. Alternatively, it has been suggested that this terrain formed as a result of the convergence of ejecta from the Calaris Basin itself. Overall, about 15 impact basins have been identified on the imaged part of Mercury. A notable basin is the 400 km wide multi-ring Kolstag basin that has an ejecta blanket extending up to 500 km from its rim and a floor that has been filled by smooth planes of material. Like the Moon, the surface of Mercury has incurred the effects of space weathering processes, including solar wind and micrometeorite impacts. MESSENGER achieved 100% mapping of Mercury on the 6th of March 2013 and completed its first year-long extended mission on March the 17th, 2013. Its second extended mission is scheduled to end later this month. Seen here, under construction in January 2015, is the next mission to study Mercury. Called the Bepi-Colombo mission, it consists of two separate orbiting spacecraft, the European Space Agency's Mercury Planetary Orbiter, MPO, and the Japan Aerospace Exploration Agency's Mercury Magnetospheric Orbiter, MMO. Mercury Planetary Orbiter will study the surface and internal composition of our solar system's innermost planet, and MMO will study Mercury's unusual, powerful magnetosphere, the region of space around the planet that is dominated by its magnetic field. The twin orbiters will also search for more signs of possible water ice in some of Mercury's permanently shadowed craters. Let us now turn our attention to Venus, a planet equal in size to the Earth and our twin in the solar system. The planet Venus is named after the Roman goddess of love and beauty. It is the second planet in order of remoteness, lying at a mean distance of 108 million kilometres and takes 224.7 days to complete its path around the Sun. Venus is 12,111 104 kilometers in diameter, and mysteriously this planet is upside down compared to the rest of the planets in our solar system. The axial tilt is 177 degrees. This means that the south pole of Venus is uppermost and the planet rotates backwards. The only other planet with a large axial tilt is Uranus at 97.7 degrees. Stranger still, the planet's axial rotation of 243 days is longer than the planet's year, and Venus has a very weak magnetic field. Like Mercury, Venus lies inside Earth's orbit and shows a series of phases similar to our Moon. And on rare occasions, when the Sun, Venus and Earth line up, it can be seen transiting across the face of the Sun. The planet Mercury will next transit across the Sun on the 9th of May 2016, while we'll have to wait until the 11th of December 2117 for the next transit of Venus. Much of what we have learned about Venus today comes from observations and findings returned from visiting spacecraft, including the European Venus Express mission. The atmosphere is mainly composed of thick, dense clouds of carbon dioxide, about 96.5%, followed by nitrogen, 3.5%, with small amounts of water vapour, carbon monoxide, helium, argon and neon. Only 2% of the sunlight arriving at Venus reaches the surface below, as the cloud droplets are highly reflective. The daylight on the planet is similar to the Earth's at twilight and is distinctly of a yellowish hue. There is also a constant rumble of thunder in various locations around Venus and a drizzle of sulfuric acid droplets, so it is a very hostile environment. It was not until the 1st of March 1966 that Venera 3 became the first man-made object to impact the surface of another planet, although its scientific payload malfunctioned and it returned no data. Venera 4 fared better and succeeded on the 16th of October 1967 in delivering the first results on temperature and pressure in the atmosphere. Atmospheric pressure is measured by comparing Earth's at ground level, which averages 1030 millibars or 1 atmosphere, with that on Venus. The first successful landings were by Venera 5 and 6 on the 16th of May 1969. Once down, they returned data including atmospheric compositions along with the temperature and pressure from the surface. Each lander survived for just under an hour before being overcome by the higher temperatures and pressures. So there could be no doubt that the surface was very hot, and there was a measured value for the surface pressure at last, nearly 93 Earth atmospheres. The two go together. The high pressure is the main reason for the hellish temperature and the reason the environment differs so much from the Earth. The later Soviet missions to the surface, starting with Venera 9 on the 22nd of October 1975, obtained remarkable photographs of the terrain. These pictures were obtained in natural light when it was found that enough of the sunlight arriving at Venus could diffuse through the clouds to the surface to illuminate the scene. Mariner 10 carried a sophisticated camera, so the Venus encounter offered the chance to carry out the first detailed photographic survey of the planet from close range. As anticipated, the ultraviolet filter delivered the best contrast and revealed details in the cloud structure on all scales, from planet-wide to the smallest details observable. a few kilometres across. The big sideways Y feature that astronomers had followed for decades was there, but also a host of more intricate structure, including cloud patterns suggesting waves and turbulence and some rather strange linear features. The Y was revealed as a combination of large-scale planetary waves that seem to embrace a subsolar point, where the Sun is directly overhead. Here, convective boiling activity is seen to be present in the cloud patterns. The rapid circulation of the ultraviolet dark features around the equator at speeds of over 100 meters per second was also quite obvious in sequences of images taken several minutes apart. The cloud tracking experiment also showed equator to pole motions, much slower than the horizontal zones running east to west, and dark features spiralling in towards the poles themselves, where the rapidly circulating air descends into a giant vortex. In 1978, radiometers on the Pioneer Venus probes found that 2% of the total sunlight falling on the planet actually reaches the surface without being absorbed. This is much less than on Earth, where the figure is about 50%, but surprisingly large considering the thickness and cloudiness of the atmosphere. In fact, it could have been realised from the brightness of Venus as seen from outside that the cloud droplets must be very reflective. They diffuse the radiation thoroughly by scattering each photon dozens of times during its passage through the atmosphere, but do not absorb as strongly as terrestrial clouds would, because they have a different composition and hence different optical properties. In March 1981, Venera 13 and 14 touched down in Phoebo Regio, carrying the first working colour cameras. Both landed on flat plains of solidified volcanic lava, but the Venera 13 site is thought to be older, since it has apparently been buckled into shallow ridges by movements of the crust to produce a suggestion of low hills in the distance. Like the earlier scenes, the closest terrain is fractured and eroded to form dark gravel patches. The rocky surface under the landers was studied with a number of instruments, some devised to survive the heat so they could be mounted on the side of the spacecraft. The drills collected material from a few centimetres down and transferred it into a sample chamber containing an X-ray fluorescence spectrometer. The results at both sites indicated a composition similar to terrestrial basalts, confirming that it is material from volcanoes. Basalt comes in many forms on Earth, and it is not the same everywhere on Venus. A higher content of potassium was found in the volcanic rock at the Venera 14 site than in the other areas. Other instruments on the later Venera landers, principally gamma-ray spectrometers, provided information on the density and chemical composition of the surface rocks where they landed, finding that the abundances of the naturally radioactive elements of uranium, thorium and potassium were again consistent with the composition within the range found in volcanic rocks here on Earth. Venus Express was launched in November 2005 and arrived at Venus in April 2006, where it began continuously sending back science data from its polar orbit around the planet. Equipped with 7 scientific instruments, the main objective of the mission was the long-term observation of the Venusian atmosphere. The spacecraft has made a number of interesting discoveries over the last decade. Venus is well known for its remarkable super-rotating upper atmosphere, which sweeps around the planet once every 4 Earth days. This is in stark contrast to the rotation of the planet itself, the length of the day, which takes 243 Earth days. After its arrival at the planet in 2006, Venus Express was able to conduct the most detailed survey of the cloud motions in the atmosphere of Venus, with the surprising discovery that the planet's high-level winds have become faster over time. On top of this long-term increase in the average wind speed, studies have also revealed regular variations linked to the local time of day and the altitude of the Sun above the horizon, as well as the rotation period of Venus. There has also been dramatic variations in the average wind speeds observed between consecutive orbits of Venus Express around the planet. In some cases, wind speeds at low latitudes varied such that clouds completed one journey around the planet in 3.9 days, while on other occasions they took 5.3 days. The existence of the polar vortices on Venus has been known for many years, but high-resolution infrared measurements obtained by the visible and infrared thermal imaging spectrometer (VIRTIS) instrument on Venus Express have revealed that the southern vortex is far more complex than that previously believed. The new observations show that the centre of the vortex has a highly variable shape and internal structure, and its morphology is constantly changing on timescales less than 24 hours as a result of differential rotation. This fast-moving feature is all the more surprising since its centre of rotation is offset from the geographical South Pole. The images show that the core of a dynamic southern vortex can take almost any shape, so although it often looks like an S or figure 8, it may become completely irregular or even chaotic in appearance. These rapid shape changes indicate complex weather patterns, which are strongly influenced by the fact that the centre of the vortex does not coincide with the geographical pole. Images from the Venus monitoring camera and from the VIRTIS instrument show that the speeds of the zonal winds change with latitude, so that the vortex is continuously being pulled and stretched. Although the mean zonal wind is retrograde, that's blowing from east to west, its speed decreases towards the pole. The centre of rotation drifts right around the pole over a period of 5 to 10 Earth days. Its average displacement from the South Pole is about 3 degrees of latitude, or several hundred kilometres. Venus Express also discovered an unexpected cold area in the Venusian atmosphere. The unexpected cold layer is far colder than any part of Earth's atmosphere, despite Venus being much closer to the Sun. The discovery was made by studying light from the Sun as it passed through the atmosphere, revealing the concentration of carbon dioxide gas molecules at various altitudes along the terminator, the dividing line between the day and night sides of the planet. Armed with information about the concentration of carbon dioxide and data on atmospheric pressure at each height, scientists could then calculate the corresponding temperatures. Since the temperature at some heights dips below the freezing temperature of carbon dioxide, the main constituent of the atmosphere, carbon dioxide ice may be able to form there, possibly forming clouds of ice or snow particles. The data also shows that the cold layer above the terminator is sandwiched between two comparatively warm layers. The temperature profiles on the hot day side and cool night side at altitudes above 120 kilometres are extremely different, so the terminator is affected by conditions on both sides. The night side may be playing a greater role at one altitude, and the day side might be playing a larger role at other altitudes. This situation is unique to Venus, since the temperature profile along the terminator in the atmospheres of Earth and Mars are very different. Although Venus has no magnetosphere to deflect the charged particles of a solar wind, electrons and protons, as they stream past the planet. It is partially protected from the erosion of the outer atmosphere by an induced magnetic field arising from the interaction of the solar wind and the planet's ionosphere. As on Earth, solar ultraviolet radiation removes electrons from the atoms and molecules in the upper atmosphere, creating a region of electrically charged gas known as the ionosphere. This ionized layer interacts with the solar wind and the magnetic field carried by the solar wind. Until now, magnetic reconnection was not generally thought to occur near non-magnetized planets, so scientists were surprised when Venus Express found the first evidence of this process. Reconnection converts magnetic energy into kinetic energy in the form of accelerating particles and occurs when oppositely directed magnetic field lines break and connect with each other. On Earth, it is responsible for magnetic storms and polar aurora. At Earth, the process occurs at a distance of about 10 to 30 planetary radii. Since Earth's magnetosphere is 10 times larger, reconnection at Venus will be expected to occur 1 to 3 radii, or 23,000 kilometres down its tail, precisely where Venus Express detected the reconnection events.
Venus doesn't have a magnetic field. So Venus is just this big rock with this atmosphere and the ionosphere sitting in space, and the supersonic solar wind with the interplanetary magnetic field whacks into Venus, and it can't penetrate through the ionosphere. So the interplanetary field lines just sort of pile up ahead of Venus, like cars on a freeway. The solar wind whacking into it essentially sort of strips off the atmosphere, and it literally forms this long tail, like a comet, but stretching out into space. Pioneer Venus Orbiter was the first spacecraft to really thoroughly explore that night side region where the atmosphere is all escaping away, and it discovered this really mysterious phenomena which has yet to really be explained. Imagine that we're flying from pole to pole on the night side, so we're feeling the plasma around us, and then suddenly the ionosphere disappears, and then it sort of comes back. And this is what an ionospheric hole is. It's like a chasm in the sky, a big hole where the ionosphere is just absent. So Pioneer Venus Orbiter basically measured inside these things, and we saw that there is very little plasma, and there's all this magnetic field. And from that, they sort of suggested that this is essentially a magnetic structure that's sitting in the night side. I wanted to see if I could go looking for these things with Venus Express. What we saw is essentially this really exciting, strong, straight magnetic field lines that we expected, and really boring plasma signatures. It shows us that this is a magnetic structure, right? This is a tube of interplanetary magnetic field that, well, PVO saw it coming out of the ground, and now we've seen it way out in the tail. So these things really continue out to much higher altitudes than we previously have found them at. And the other thing that's important is, well, Pioneer Venus Orbiter only saw them during solar maximum, when the sun was really disturbed and really blowy and stormy. But we've now been seeing them all throughout the solar cycle. There's sort of two explanations for what might be causing this. One possibility is that so these field lines, then they come in from space and they get sort of stuck in the ionosphere. The ionosphere sort of flows from the day side to the night side, and as it goes around, it sort of meets this plasma that's in the tail, and there's sort of a pile-up between the two. So that's one idea. And the other idea is that on the day side, the field lines come in and they actually sink through the ionosphere, go through the rocky mantle, and then get hung up on this big metallic core. These field lines essentially end up draping around the core and stick out the rock at the back. One of the main differences between Venus and the Earth is simply that Venus doesn't have a magnetic field. So the way it interacts with the star is completely different. If you want to understand how did Venus get that way, why does Venus not have any ocean, you need to understand the interaction between the star and the planet.
Venus Express also discovered that surface features were not quite where they should be, evidence that Earth's cloud-covered neighbour spins a little slower than previously measured. Using the Virtus instrument at infrared wavelengths to penetrate the thick cloud cover and study the surface, scientists discovered that some features were displaced by up to 20 kilometres from where they should be. The Magellan spacecraft, also known as the Venus Radar Mapper, was a space probe launched by NASA on May 4th, 1989 to map the surface of Venus by using synthetic aperture radar and to measure the planetary gravitational field. Over its 4-year mission, NASA's Magellan orbiter was able to watch surface features rotate under it, allowing scientists to determine that the length of the day on Venus was 243 Earth days. However, the landforms seen by Venus Express some 16 years later could not be lined up with those observed by Magellan if the length of the Venus day is on average 6.5 minutes longer. Scientists have looked at the possibility of this change arising from short-term random variations in the length of a Venus day, but have concluded that these should average themselves out over time. On the other hand, atmospheric models have shown that the planet may have weather cycles stretching over decades, which could lead to equally long-term changes in the rotation period. These detailed measurements from orbit are helping scientists determine whether Venus has a solid or liquid core, which will help our understanding of the planet's formation and how it evolved. If Venus had a solid core, its mass must be more concentrated towards the centre. In this case, the planet's rotation would react less to external forces. The most important of these external forces is associated with a dense atmosphere and high velocity winds. After 8 years in orbit, the European Space Agency's Venus Express completed its routine science observations in May 2014 and made a series of plunges into Venus's atmosphere in an experimental procedure called aerobraking. over a period of a month, the spacecraft surfed in and out of the atmosphere at altitudes typically between 131 kilometres and 135 kilometres for a couple of minutes on each of its closest approaches to the planet. Before, normal operations involved an elliptical orbit every 24 hours that took Venus Express from 66,000 kilometres over the South Pole down to around 250 kilometres at the North Pole, just above the top of the atmosphere. Aerobraking can be used to reduce the speed of a spacecraft approaching a planet or a moon with an atmosphere, allowing it to be captured into orbit and to move from an elliptical orbit to a more circular one. Less fuel has to be carried, yielding benefits all round. The technique will be used on future missions, and the Venus Express experiments will help guide their design.
Since 2005, ESA's Venus Express has been in orbit around Venus, scanning its atmosphere from above. Now, to take a better look, ESA has sent Venus Express skimming into the top layer of the atmosphere using a technique known as aerobraking.
We went into the atmosphere in this direction because this face of the spacecraft, which had been attached to the rocket originally when it was launched, was most able to take the forces and the temperatures. We also turned the solar panels to maximize the amount of friction and to get the most amount of braking.
This maneuver offered the first ever close-up view of Venus's upper atmosphere, and it wasn't what was expected.
What we saw that was a little unusual is the variability in the pressure, as if there were waves within the atmosphere. And so that possible wave-like structure was not expected. And analyzing that data will keep scientists busy for a little while yet.
Thanks to Venus Express's data, it's thought that these wave-like fluctuations could be related to the speed of the winds that circulate around Venus. And these winds appear to be getting faster.
When we arrived at Venus 8 years ago, we detected winds at 300 kilometers per hour, very fast. But what has happened during these years, until now, they have actually increased. We now see winds of 400 kilometers per hour. And we can't really explain why that has happened.
Venus Express has spent more than 8 years digging into the secrets of the Venusian atmosphere to better understand the complex dynamics between the planet's atmosphere and interplanetary solar winds and the atmosphere and the surface. While these recent findings pose many new questions, it is possible that clues to the answers lie somewhere in the vast amounts of data that have been gathered by the spacecraft over the course of its mission.
The results of the experiment show that the atmosphere seems to be more variable than previously thought for this altitude range. Between altitudes of 165 kilometres and 130 kilometres, the atmospheric density increases by a factor of roughly 1,000, meaning that the forces and stresses encountered by Venus Express were much higher than during normal operations. It also experienced extreme heating cycles, with temperatures rising by over 100 degrees centigrade during several 100-second-long passes through the atmosphere. In addition, the atmospheric drag at these lower altitudes was so great that the spacecraft's orbital period was reduced by more than an hour. At the end of the aerobraking experiment, 15 thruster burns raised the craft's altitude, preventing it from dropping into the atmosphere. This month, with no fuel left to keep it aloft, Venus Express will plunge into the planet's hostile clouds and then impact onto the planet's surface. The mission has been very successful. NASA would like to send a manned mission to Venus. NASA have come up with HAVOC, HAVOC, or High Altitude Venus Operational Concept, a light-of-an-air rocket ship that would help send 2 astronauts on a 30-day mission to explore the planet's atmosphere. Exploration of Venus is a challenge not only because its acid-lace atmosphere, but also its extremely hot surface temperature and extremely high pressure on the ground. As the Venus Express mission ends, we now know more about the Earth's twin than since the dawn of the space age. Back then, there was even speculation there could be Amazon-like rainforests, lakes, and even life on the planet. How wrong we were. That is all we have time for this month. Please visit our website, Vimeo, where you can watch all of the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.